Thank you. All right, yeah, my name is Arvid, and this year marks the 20th anniversary of a side project that I started, libtorrent. So, 2004, the BitTorrent scene at the time was there was a Python implementation and there was a Java implementation, very feature-rich. Notably, there were no C++ implementations, as far as I know, at least. There was another C++ implementation the following year, 2005, also called libtorrent, unfortunately to me. But so libtorrent is a C++ library implementing the BitTorrent protocol. It is used and has been used by various programs over the years. Some of these are pretty old and not really maintained anymore. There are some just plain BitTorrent clients and some games. My favorite, I don't have a logo for it, is GeneTorrent, which was used to distribute sequenced cancer genomes to universities for doing cancer research. All right, I'm going to start with a brief 3-slide introduction to the BitTorrent protocol. Or high level. Imagine you have a file.txt, you chop it up into small pieces, and you compute the SHA-1 hash of each piece. Along with those hashes, you store the size of each chunk or piece, the name of the file, and the total size. Note that the last bit is not necessarily a full piece. That's why you need the total size of the file as well. When you start downloading or uploading this file, every peer needs this metadata file or torrent file, which has the hashes in them. So you discover peers through various means. You connect to them, and in the handshake, you say, I have these pieces, and correspondingly, you know which pieces the other end has. You start requesting pieces that you want, and whenever you get a piece, you validate or you verify the hash against your metadata to make sure that it's correct. And then you keep advertising that you have new pieces so that everyone knows which pieces everyone else has. Notice that in this protocol, there's no, the connections are symmetrical. There's no client server. Everyone is sort of the same. You handshake, you use the same message to handshake, and you request, both ends use the same message to request, and so on. And then, to make this all work, there are a lot of nitty-gritty details. For instance, to discover peers, you might use a distributed hash table, which is an entirely separate sort of overlay where peers talk to each other. There's a transport protocol based on UDP. In addition to TCP, you can use both. There are some certain incentives for people to share so that you don't just sort of free ride and just download. There are algorithms for picking which pieces you should download first to maximize the health sort of this swarm or collection of peers. You might need to ban peers that send you corrupt data. You know, you validate all the data against the SHA-1 hashes. And you might need to handle disk I/O efficiently because there's going to be a lot of random access reads and writes to disk. So there are plenty of interesting areas to sort of dig into. It's one of the reasons this project has stayed interesting for so long.
Ban peers over TCP more than over UDP, or one case it's guaranteed to be intentional, the other case it might be.
So the question was about the transport protocol. So UTP, the transport protocol that sits on top of UDP, implements all of the important features that TCP does. The important distinction is that instead of using congestion control that's only based on packet loss, it uses one-way delays as well, so that you don't suffer from buffer bloat, essentially, if your modem send buffer is too big. Anyway, I was going to mention dig into one little detail of this, specifically around maximizing the transfer rate, something that's is a core interest when using BitTorrent or similar protocols. Specifically maximizing utilization of available network capacity. So first I would like to introduce a concept called bandwidth delay product. Bandwidth delay product can be visualized as, imagine a pipeline or a pipe of some kind. You have a bandwidth, which is sort of the width of the pipe, and you have a length of the pipe, which is the delay. So if you start pouring water in one end, it's going to take a certain amount of time for it to arrive in the other end. And the width of the pipe limits how much water you can put in at a time. So this is an analogy of how a network connection between two peers operates. So imagine the sender starts sending packets with a certain pace. If you send them one at a time, you send one, or maybe in this case, you send 2 packets, and then you wait for the recipient to tell you that they arrived before you send the next one. You might not utilize the network capacity very well. You might not fill the pipe, so to speak. So it's suboptimal. What you would like to do is to make sure that you fill, that every possible space in this pipe is full of packets. So the size of all of these packets is the bandwidth delay product. You multiply the delay with the bandwidth, essentially. So in order to maximize, you need to make sure that the number of packets that you have in flight at any given time is at least the bandwidth delay product. To visualize this a little bit, you can think of it, you can compare it to how HTTP would work compared to BitTorrent. In HTTP, typically, you have a single request for one file, and then the server sends back that entire file. So you have something like one request, and then the entire file comes back. Whereas in BitTorrent, you send a request for each little chunk. You don't ask for the entire file. So you have multiple requests instead of one, which means that the responsibility to fill the pipe is no longer just the senders, but it's also the receivers. The receiver need to make sure that there are sufficient number of requests in flight to fill the pipe. So imagine if you send one request at a time, you get something like this. Suboptimal utilization of the network capacity. You want something like where you pipeline requests, so you have multiple in flight, something that looks like this. The downloader just keeps sending requests, so the uploader can keep saturating the link. The other aspect is what constitutes the delay. So in practice, it's not just the one-way delay. It's the delay it takes for you to send the request to receiving the response. That's when you can send the next request. So this is a diagram. Time progresses down. You have the downloader to the left and the uploader to the right. The downloader sends a request for a piece. Some time passes because of the propagation delay through the network. But then the uploader needs to possibly queue up a disk read for this request. It might have to seek on the disk, if it's a spinning disk, and read off the bytes, and then form a packet and send it back. So it's not just the propagation delay in the network that you have to account for in order to fill the bandwidth delay product. Additionally, the time it takes on the uploader side can vary widely. If you have a cache hit, for instance, you might already have this piece of memory, this content in memory, then you can just respond with it right away. So responses come back out of order. Also has to be taken into account. So as the downloader, you must make sure that you just keep sending piece requests in order to have to let the uploader fill the response pipe. If the downloader doesn't send enough, then it's up to the uploader to make sure that this latency is minimized. The latency from receiving a request to sending it back. If that latency is too high, then you're still not going to fill the pipe because you're going to basically just sit around waiting for the disk. So how many requests should you have outstanding at any given time? If you have too few, then you don't maximize throughput. But if you have too many, then there are like many small issues. For instance, you might limit the number of peers you can request concurrently from, for instance. If you think of the extreme case where you request everything from a single peer, and then another peer appears on the swarm, you've already sort of allocated all of these requests from this other peer. There's nothing left to request, so then you end up downloading everything from one peer, which is suboptimal. But typically, it's better to overshoot and have too many outstanding requests than too few. So one solution to this is to continuously update the number of outstanding requests that you want based on the download rate times some queue time. That's just like a magic number that you configure, say 3 seconds. So for example, you can think if you configure the queue time to be 3 seconds and you have a download rate of 30 blocks per second, then you want to have 90 outstanding requests at any given time. So if you have a peer that's sending you blocks slowly, then you have fewer outstanding. If you have a peer that's sending you blocks quickly, you need more outstanding requests. There are a few risks with this. For instance, the download rate is affected by the number of outstanding requests. So there's like a potential feedback loop here. If your number of requests is too low, then that's going to keep your download rates down. So the queue time kind of has to be set pretty aggressively. And then it will then steadily increase. The download rate will increase. You will increase the outstanding requests. The download rate increases again. So it like gradually improves or increases the download rate. But it's kind of linear, so it might take a long time. If you have a very fast connection, it might take a very long time to reach, especially if you have a high bandwidth, high latency connection. It might take a long time to actually saturate that link. So one other trick that we can borrow from the transport protocol world is slow start. This is a concept that exists in TCP as well. So when you first start out a connection to a new peer that's unknown, you double the outstanding requests. So every time you receive a piece of payload back, you send 2 requests. So you get those 2 backs, you send 4 requests, and so on. So every round trip, you double the number of requests. That's going to quickly ramp up until you sort of enter a steady state where the download rate no longer increases. Then there's no point in increasing the number of outstanding requests. Then you enter this steady state of determining the outstanding requests by the download rate. But that's not all. That's sort of the low level of maximizing transfer rate. The other one is bandwidth allocation. When you have many peers, how do you decide where your bandwidth, specifically upload bandwidth, should go? The way BitTorrent works is that you don't always upload to everyone. By default, when you first connect to a peer, you're not allowed to make piece requests. You have to be unchoked, is the term. And so you can be unchoked, which is the permission for you to make requests, or you can be choked, which is revoking that permission, so you can no longer make requests. So there's a question of how do we decide which peers to choke and to unchoke? So that's the algorithm called tit for tat, which was kind of a groundbreaking idea, I think, for BitTorrent when it came out. This creates an incentive to basically stabilize the network and disincentivize free writing that drains the network of its capacity. So the way it works is every 15 seconds, you order all of your peers by the number of bytes that they sent you in this last round. So every 15 seconds is like a round. You count the number of bytes they've sent you in the last 15 seconds, you sort them, and then you pick the top, the ones that sent you the most bytes. Those are the good ones. And then you unchoke those. So you let those make requests to you, and the other ones you choke. So imagine we have a bunch of peers, and they sent us this many bytes in the last 15 seconds, and they're ordered, right? So the ones that sent us the most are at the top, and we say n is 4. We pick the top 4 ones, and we unchoke those, and we choke everyone else.
How can you get started when you don't have anything to share?
Yeah, there's a little asterisk down here. There's a separate mechanism where you unchoke 1 or 2 peers unconditionally for a longer period of time, just to try them out, to see if they might be better than anyone else. And then if they are, then they get promoted in the next round, basically. So this creates an incentive to share. So when you participate in a swarm, you have an incentive to upload, and it disincentivizes free writing. It makes it slightly harder to just download from people without uploading anything. Yes?
How do you find the balance between serving everybody and your memory, in a sense like cache? For instance, if people receiving from one peer, they have a lot of stuff in the memory subsystem, right? But if you can serve everybody, then you can trash your memory as well. Or how does it? Is it different? Your memory subsystem is like.
So typically you don't keep things around in memory for very long. So when you download from someone, you try to write it to disk as soon as possible. You might keep it around in memory also for cache purposes, in case you think it's likely that someone else will request it. But there isn't really a connection between who you downloaded something from and whether it's in memory or not. You download it and then you queue it up to be written to disk.
Does it use memmap?
That's a whole talk of itself. libtorrent does use mmap as of in the most recent release, which is quite old by now. It doesn't work as well as one would hope. Certainly not as well as I would hope. There are alternatives. You can use like plain POSIX calls right now, but it's not very sophisticated. Older versions are a bit more complex, where there's a thread pool of more sophisticated low-level disk I/O. So that's one of the big projects that I've been working on lately to improve the disk subsystem. But for sorry.
Sorry, in slow start, what happens if your first packet is corrupted?
Typically, you don't actually validate. The validation happens at a different timescale, essentially. Typically, even you don't validate individual packets. In the original version of the BitTorrent protocol, you have pieces that are larger than the requests. So you need to request maybe 16 or 128 or 256 blocks or chunks until you have enough to actually validate the SHA-1. So that happens much later. But typically what happens is, if a peer sends you data that's corrupt, then you ban them, and you disconnect and you prevent them from connecting again. So that's pretty effective. The only reason you would receive corrupt data are because of mistakes. I think that it doesn't work as a malicious sort of attack. Yes.
Speaking of the checking the SHAs, during the tit for tat algorithm, are you counting the kind of validated blocks, or is this just the number of bytes you receive?
It's counting all of the payload bytes, but regardless of whether they are validated or not, because the validation happens sort of on a separate timescale. But just plain protocol messages don't count, obviously. It's the payload messages. All right, so given this, there's an interesting question. How do you choose n? Also, by the way, you can sort of think of this as a blind auction that happens every 15 seconds. You sort of place your bid by deciding how much to upload to someone or how fast to upload. And then if you win, you get rewarded with being unchoked or remaining unchoked, perhaps. So you can keep downloading from them. But how you choose n is not trivial. Because perhaps this is supposed to be an illustration. Going back to the pipe analogy, imagine, so we are the peer at the bottom, the yellow rectangle. Imagine we have a very wide internet connection, but the other peer has a very narrow internet connection. And we try to upload to them as fast as possible. It might be limited by their capacity and not ours. But it could also be that we have a narrow connection and they have a wide connection that's limiting our bandwidth. And it's not trivial to tell the difference, whether it's our end or their end that's limiting the bandwidth. So, for instance, if we are uploading to 3 peers, imagine that we have a high bandwidth connection, and the 3 peers we're sending to have a low bandwidth connection. We saturate their links, but we are far from saturating our own link. In this scenario, we would definitely want to upload to more peers, so we would like to increase n. But maybe we're in the opposite situation, where we have a narrow upload capacity, and we're uploading to 7 peers. Did I count it right? So we're not even close to saturating their capacity. In this scenario, we would like to decrease the number of peers that we're uploading to be more efficient, and also to make it more likely that each of them reciprocate by unchoking us. Because right now, we're spreading our bandwidth thin. Basically, we're participating in too many auctions, and we don't have enough bandwidth to make a good bid in any of them. So this is a challenge. How do you pick n? There are no excellent answers to this question. The way most BitTorrent clients do this is to just have a fixed number, and it's typically 4. And you can change it in your configuration. So if you have a fast internet connection, you might want to increase that to a higher number. Another interesting option is to optimize the number. There was a paper by Thomas Isdal and Michael Piatek out of UW from 2007, so it's a long time ago, where they experimented with really focusing on this as an auction, and they would change the upload rate that they would send to peers and try to detect where the cutoff is, where they will choke you and unchoke you. So they would send you just enough for them to unchoke you. Then you would take the leftover bandwidth that you have and use it for more peers. So you could detect exactly what the return on investment was to send data to one peer. There are some problems with this approach if everyone does it, because then it kind of becomes a race to the bottom where everyone just keeps lowering.
Is that why some trackers banned some clients back in the day? I remember some trackers you connect and you just got like bitcommit sucks disconnected.
I don't know why clients would be. Probably not because of this. Probably because trackers were worried about sending incorrect statistics or something like that, I'm guessing.
Private trackers, you mean?
Yeah.
Yeah, they don't like the HT.
However, a third approach is to make it rate-based. So you look at the combined upload rate that you have, or that you can achieve to all peers, and you base the number of peers that you unchoke on that. So this is the algorithm that I use in libtorrent. you look at the number of uploaded bytes by all peers in the last 15 seconds, so each round, 15-second round. So this is no longer in the choke mechanism. Then you look at you order them by download rate or the number of downloaded bytes. Here you order them by uploaded bytes. So going back to this example of peers, I use the same numbers, but this is not downloaded, this is uploaded. So the formula is 15 plus n times 30 kilobytes for a 15-second period, which means that so that sets the cutoff. Every peer that gets unchoked needs to have uploaded at least that amount. So you sort of get this sliding, like you keep traversing down the list, and as soon as the limit keeps rising, right? As n gets larger, it's raised by 30 kilobytes each peer you go down. These numbers are illustrative; they're not accurate. But for example, you might end up with the top 6 peers you could upload to at this rate. So then you decide that for this round n should be 6, and then you go through the normal unchoke algorithm and you unchoke 6 peers. You pick the 6 best peers. So that's a decent algorithm. There are obvious problems with it. If you happen to have a single peer that's very slow that you're uploading to, they might not be representative of your complete capacity. So it might also be somewhat random, and it might take a while for you to actually discover what your upload capacity truly is. That's why I'm saying that there's no excellent solution to this problem. So those were the 2 things I wanted to bring up: the slow start when it comes to outstanding requests, and picking how many peers, how thin to spread your upload capacity. Hope some of that was a little bit interesting, maybe relevant. That's all I got. Thank you. Any questions? Yes.
Well, you said that you were using the rarest chunk algorithm to decide which to download first. Are you
Yes.
using this in the caching algorithm or any caching algorithms? No, this is the rarest chunk. We should cache this because there's a possibility that other peers will want to download this.
Great question. So about rarest first. Rarest first is about among your connections, which piece is the rarest, and that's the one, or among the rarest pieces, those are the ones that you download. There's no mechanism for that at the disk cache layer, but I don't really think it's necessary, because those, like a regular LRU or an ARC cache, will have that effect anyway, because you are downloading the most recently written pieces will be the ones that are rare from your perspective already, so they will sort of be active. But you also don't necessarily know which ones are rare from all of your peers' perspective, right? It's an approximation of the global rarity, right? Yes?
How long does the slow start take actually? Because like you do it like about a third of the time you have a connection, and then wouldn't it make more sense to like keep your peers steady because you don't have to slow start it up again?
Well, so that was just an illustration. Typically, ideally, you keep your connections very long-lived, and how long it takes to slow start depends on a lot of factors. Like it's not as clean in reality, because you might get interrupted from various things. And but I did run this in a simulation back in the day when I was implementing this, and then it makes quite a big difference. You can experiment with very wide capacity and small capacity, so it depends, right? If for a low capacity connection, it doesn't really make a difference, but for a high capacity connection, that's really when it goes a lot faster. Jonas.
So earlier there were a few questions about the SHA signing and verification stuff. Do you know any interesting cases where there were attempts at sabotage, like in the beginning, maybe copyright holders or internet providers that wanted to kind of slow down or disturb?
There were attempts in the early days, but and the early implementations weren't very effective at banning peers. The thing is, as I mentioned, a piece is typically much bigger than a single request. So if you want to maximize your download rate, you want to download from multiple peers into the same piece. So once you validate a piece, you don't necessarily know who sent you the bad data. You just know that there's some bad data here. So there are some sophisticated algorithms where you can remember which peer sent what, and then you try to replace them one at a time. And at some point you figure out, like some point later, you figure out which one was the bad data, and then you can ban the peer in hindsight. And that's surprisingly effective, even though it's.
But the protocol itself was like good enough.
Yeah.
So it's kind of
Yeah. Yes.
Yeah, so basically they said that the protocol already existed, almost all, but they implemented it in C++.
Yeah.
What do you think is the benefit of re-implementing it in C++? And why do you think that the clients or the users that you showed in the beginning, why do you think that they preferred your libtorrent before the others that existed previously?
Yeah, good question. In my mind, back in 2004, I liked C++, still like C++, so that's probably the main reason. But the other implementation, both Python and Java, requires a virtual machine or an interpreter. So if you actually want to embed something, I think that can make it much easier to have a native library. And even if you don't necessarily need to embed it, if you just want to embed it, you need a library, and the other alternatives were full like applications rather than libraries. So that might also. Yeah. Yes.
Is this the raster bar version of libtorrent?
Yes, that's right. Yes.
You mentioned simulation. I just wondered, how do you test this? How does the test environment do? Do you spawn a shitload of VMs and you virtual switch and you choke the different connections? How do you physically test implementation?
Yeah, testing is really interesting. I should have mentioned that on one of the topics that are interesting. Most tests, or the simplest test, I just spawn multiple sessions within the same process that can talk to each other over a normal socket. But the more sophisticated tests, I actually implemented a discrete step simulator that implements most of the Boost ACO API. So you can build the whole thing in a simulation build configuration, and then you can spin up all of these spin up a virtual network, and you can impose bandwidth restrictions and packet loss restrictions and latency restrictions, and then you can try a lot of scenarios, basically.
That's another topic.
Yes.